Alright, let's move on to our next set of questions. Question 101. Your web application has several VM instances running within a VPC. You want to restrict communications between instances to only the paths and ports you authorize, but you don't want to rely on static IP addresses or subnets because the app can autoscale. How should you restrict communications? A. Use separate VPCs to restrict traffic. B. Use firewall rules based on network tags attached to the compute instances. C. Use Cloud DNS and only allow connections from authorized hostnames. D. Use service accounts and configure the web application to authorize particular service accounts to have access. Okay, this is a network security question about controlling traffic in a dynamic, auto-scaling environment. The main challenge is that we can't use static IP addresses in our rules, because the VMs are constantly being created and destroyed. With that in mind, let's look at our options. Let's start with option A, using separate VPCs. This is incorrect because it's an overly complex solution. It would require setting up VPC peering or VPNs just for your application's internal components to talk to each other, which is not a simple or efficient way to manage traffic. Next, option C suggests using Cloud DNS. This is also incorrect. DNS is used to resolve domain names to IP addresses. It is not a security tool that can enforce rules about which servers are allowed to communicate with each other. Option D proposes using service accounts. This is incorrect because service accounts are for identity and permissions at the application and API level. They control who can do what. They don't control network traffic at the IP and port level. That's the job of a firewall. This brings us to option B, which is the correct and Google-recommended solution. The way this works is you apply a network tag to your virtual machines. Since you're using an autoscaler, you would add this tag to your instance template. Then, you create VPC firewall rules that use these tags as the source or destination. For example, you can create a rule that allows traffic from any VM with the web tier tag to any VM with the API tier tag. Because new instances created by the autoscaler automatically get the tag from the template, your firewall rules will apply to them instantly without needing to know their IP addresses. Therefore, the best way to restrict communications in this dynamic environment is B. Use firewall rules based on network tags attached to the compute instances. Question 102. Your company is using Cloud SQL as the database backend for a large CRM deployment. You want to scale as usage increases and ensure that you don't run out of storage, maintain 75% CPU usage cores, and keep replication lag below 60 seconds. What are the correct steps to meet your requirements? 1. Enable automatic storage increase for the instance. 2. Create a Stackdriver alert when CPU usage exceeds 75%, and change the instance type to reduce CPU usage. 3. Create a Stackdriver alert for replication lag, and shard the database to reduce replication time. B1. Enable automatic storage increase for the instance. 2. Change the instance type to a 32-core machine type to keep CPU usage below 75%. 3. Create a Stackdriver alert for replication lag, and deploy Memcake to reduce load on the master. C1. Create a Stackdriver alert when storage exceeds 75%, and increase the available storage on the instance to create more space. 2. Deploy Memcake to reduce CPU load. 3. Change the instance type to a 32-core machine type to reduce replication lag. D1. Create a Stackdriver alert when storage exceeds 75%, and increase the available storage on the instance to create more space. 2. Deploy Memcake to reduce CPU load. 3. Create a Stackdriver alert for replication lag, and change the instance type to a 32-core machine type to reduce replication lag. Okay, this question requires us to find the best operational strategy for managing a growing Cloud SQL database. We need to address 3 specific requirements: storage, CPU usage, and replication lag. With that in mind, let's look at our options. Let's start by looking at options C and D. Both of these are incorrect because for the storage requirement, they suggest creating an alert and manually increasing storage. This ignores a key feature of Cloud SQL, which is the ability to enable automatic storage increases. Using the built-in automated feature is always the better and more reliable practice. Next, let's look at option B. While it correctly suggests enabling automatic storage increase, its approach to the CPU problem is not optimal. It suggests immediately changing to a large 32-core machine. This is not cost-effective. The better approach is to monitor the CPU and only scale up when necessary. Also, while Memcake can reduce read load, it's not the most direct solution for replication lag, which is often caused by heavy write traffic. This brings us to option A, which presents the most logical and comprehensive plan. For storage, it correctly uses the Enable Automatic Storage Increase feature. For CPU, it follows the best practice of creating a cloud monitoring alert to notify you when usage gets high, at which point you can react by changing the instance type. For replication lag, it also uses an alert to monitor the problem and suggests sharding the database as a valid, long-term architectural solution to reduce the load on the primary instance. Therefore, the set of steps that best meets all the requirements is a 1. Enable automatic storage increase for the instance. 2. Create a Stackdriver alert when CPU usage exceeds 75%, and change the instance type to reduce CPU usage. 3. Create a Stackdriver alert for replication lag, and shard the database to reduce replication time. Question 103. You are tasked with building an online analytical processing, OLAP, marketing analytics, and reporting tool. This requires a relational database that can operate on hundreds of terabytes of data. What is the Google recommended tool for such applications? A. Cloud Spanner because it is globally distributed. B. Cloud SQL because it is a fully managed relational database. C. Cloud Firestore because it offers real-time synchronization across devices. D. BigQuery because it is designed for large-scale processing of tabular data. Okay, this is a big data architecture question that asks us to choose the best database for an OLAP, or online analytical processing workload. The key requirements are that the solution must handle hundreds of terabytes of data and support relational-style queries for analysis. With that in mind, let's look at our options. Let's start with option A, Cloud Spanner. While Spanner is a powerful, globally distributed relational database, it is primarily designed for OLTP, or online transaction processing, workloads that require strong global consistency. It is not the recommended tool for OLAP analytics, where the focus is on running complex queries over large datasets. Next, option B is Cloud SQL. This is incorrect because Cloud SQL is a managed relational database that is not designed to scale to hundreds of terabytes for analytical workloads. It would be too slow and would not be able to handle the data volume effectively. Option C is Cloud Firestore. This is incorrect because Firestore is a NoSQL database, not a relational one. It's optimized for synchronizing data for web and mobile applications, not for large-scale data analytics. This brings us to option D, which is the correct answer. BigQuery is Google's serverless data warehouse, and it is specifically designed for this exact use case. It is built to run fast SQL queries on massive multi-terabyte datasets. Although it's not a traditional relational database, it works with tabular data and a SQL interface, making it the perfect fit for OLAP, marketing analytics, and reporting. Therefore, the Google recommended tool for this application is BigQuery, because it is designed for large-scale processing of tabular data. Question 104. You have deployed an application to Google Kubernetes Engine, GKE, and are using the Cloud SQL proxy container to make the Cloud SQL database available to the services running on Kubernetes. You are notified that the application is reporting database connection issues. Your company policies require a postmortem. What should you do? Use Cloud SQL instances restart. B. Validate that the service account used by the Cloud SQL proxy container still has the Cloud Build Editor role. C. In the GCP console, navigate to Stackdriver logging. Consult logs for GKE and Cloud SQL. D. In the GCP console, navigate to Cloud SQL. Restore the latest backup. Use kubectl to restart all pods. Okay, this is a troubleshooting question for a common architecture using GKE and Cloud SQL. The most important part of the question is the requirement for a postmortem. This means our goal isn't just to fix the problem, but to understand exactly why it happened. With that in mind, let's look at our options. Let's start with the options that suggest restarting things, like A and D. Restarting the Cloud SQL instance or the application pods might temporarily solve the connection issue, but it's a poor troubleshooting step. It doesn't help you find the root cause, and it can even destroy valuable log information that you need for your postmortem analysis. Restoring from a backup, as mentioned in D, is also an extreme measure for a connection issue and could lead to data loss. Next, let's look at option B. This suggests checking the Cloud Build Editor role. This is incorrect because that specific IAM role is for managing build processes in Cloud Build and has no permissions related to connecting to a Cloud SQL database. This brings us to option C, which is the correct first step for any proper investigation. Cloud Logging, formerly known as Stackdriver, is the centralized logging service for Google Cloud. It automatically collects logs from both your GKE application and your Cloud SQL database. By navigating to Cloud Logging and consulting the logs from both services around the time of the incident, you can find the specific error messages and events that will tell you the root cause of the connection failure. This is an essential step for any postmortem. Therefore, the correct thing to do to begin your postmortem is C. In the GCP console, navigate to Stackdriver Logging and consult the logs for GKE and Cloud SQL. Question 105. Your company pushes batches of sensitive transaction data from its application server VMs to Cloud Pub/Sub for processing and storage. What is the Google recommended way for your application to authenticate to the required Google Cloud services? Ensure that VM service accounts are granted the appropriate Cloud Pub/Sub IAM roles. B. Ensure that VM service accounts do not have access to Cloud Pub/Sub, and use VM access scopes to grant the appropriate Cloud Pub/Sub IAM roles. C. Generate an OAuth 2 access token for accessing Cloud Pub/Sub, encrypt it, and store it in cloud storage for access from each VM. D. Create a gateway to Cloud Pub/Sub using a Cloud function, and grant the Cloud Function Service account the appropriate Cloud Pub/Sub IAM roles. Okay, this is a very important security and identity management question. It's asking for the best and most secure way for an application running on a compute engine virtual machine to authenticate to other Google Cloud services, like Cloud Pub/Sub. With that in mind, let's look at our options. Let's start by looking at option B, which suggests using VM access scopes. This is incorrect because access scopes are a legacy method for granting permissions. The modern, secure, and Google-recommended best practice is to use specific IAM roles attached to a service account, as they are much more granular and flexible. Next, option C proposes manually generating an OAuth 2 token and storing it in cloud storage. This is also incorrect and a bad security practice. You should avoid manually managing credentials like tokens or keys whenever possible, as it increases the risk of them being exposed. The cloud provides a much better automated way to handle this. Option D suggests creating a gateway using a cloud function. While technically possible, this is an overly complex and inefficient architecture. It adds an unnecessary component which increases latency and cost when the VM application can and should connect directly. This brings us to option A, which is the correct and Google-recommended way. The standard practice is to use a VM service account. You create a service account, which acts as an identity for your application. You then grant that service account the specific IAM roles it needs, for example the Pub/Sub publisher role, following the principle of least privilege. When your application runs on the VM, it automatically authenticates as that service account and inherits its permissions, allowing it to securely connect to Pub/Sub without any need for manual credential management. Therefore, the Google-recommended way is ensure that VM service accounts are granted the appropriate Cloud Pub/Sub IAM roles. Question 106. Your company is moving 75 terabytes of data into Google Cloud. You want to use cloud storage and follow Google-recommended practices. What should you do? A. Use VPC network peering between the VPC and the on-premises network. B. Expose the VPC to the on-premises network using IAM and VPC sharing. C. Create a global cloud VPN gateway with VPN tunnels from each region to the on-premises peer gateway. D. Deploy cloud VPN gateway in each region. Ensure that each region has at least one VPN tunnel to the on-premises peer gateway. Okay, this question is about designing a reliable network connection for an application that is spread across multiple regions. The key to solving this is understanding that cloud VPN gateways are regional resources in Google Cloud. With that in mind, let's look at our options. Let's start with option A, which suggests using VPC network peering. This is incorrect because VPC peering is used to connect two Google Cloud VPC networks to each other, not to connect a VPC to an on-premise network. Next, option B suggests using IAM and VPC sharing. These are tools for managing permissions and sharing networks between projects within Google Cloud. They are not used to establish the actual network connection to an on-premise location. Option C is also incorrect because it mentions a global cloud VPN gateway. This type of resource does not exist in Google Cloud. VPN gateways must be created within a specific region. This brings us to option D, which is the correct and recommended architecture. Because VPN gateways are regional resources, you must deploy a separate cloud VPN gateway in each of the two regions where your application is running. You would then create VPN tunnels from each of those gateways to your on-premise network. This ensures that the instances in both regions have a reliable and redundant path to communicate with your on-premise systems. Therefore, the correct way to deploy the VPN is D. Deploy a cloud VPN gateway in each region and ensure that each region has at least one VPN tunnel to the on-premises peer gateway. Question 107. Your applications will be writing their logs to BigQuery for analysis. Each application should have its own table. Any logs older than 45 days should be removed. You want to optimize storage and follow Google recommended practices. What should you do? A. Configure the expiration time for your tables at 45 days. B. Make the tables time partitioned and configure the partition expiration at 45 days. C. Rely on BigQuery's default behavior to prune application logs older than 45 days. D. Create a script that uses the BigQuery command line tool BQ to remove records older than 45 days. Okay, this is a question about data lifecycle management in BigQuery. The goal is to find the most efficient and automated way to delete old log data to save on storage costs, following Google's recommended practices. With that in mind, let's look at our options. Let's start with option A, which suggests setting an expiration time on the entire table. This is incorrect because it would delete the whole table, including the new logs, after 45 days. We want to delete only the old logs, not the entire table. Next, option C suggests relying on BigQuery's default behavior. This is incorrect because BigQuery does not have a default behavior that automatically deletes old data. You must configure this yourself. Option D proposes creating a script to delete old records. While this is technically possible, it's not the recommended practice. It would require you to manage a server to run the script, and running delete queries can be less efficient and more costly than using BigQuery's built-in features. This brings us to option B, which is the correct and most efficient solution. The recommended practice is to first make your tables time partitioned. This organizes your data into daily chunks based on a timestamp. Then you simply configure a partition expiration of 45 days on the table. With this setting, BigQuery will automatically and efficiently delete any daily partition that is older than 45 days, without you needing to run any scripts or queries. This is a fully automated, serverless, and cost-effective way to manage your data lifecycle. Therefore, the best thing to do is B. Make the tables time partitioned, and configure the partition expiration at 45 days. Question 108. You want your Google Kubernetes Engine cluster to automatically add or remove nodes based on CPU load. What should you do? A. Configure a horizontal pod autoscaler with a target CPU usage. Enable the cluster autoscaler from the GCP console. B. Configure a horizontal pod autoscaler with a target CPU usage. Enable autoscaling on the managed instance group for the cluster using the cloud command. C. Create a deployment and set the max unavailable and max surge properties. Enable the cluster autoscaler using the cloud command. D. Create a deployment and set the max unavailable and max surge properties. Enable autoscaling on the cluster managed instance group from the GCP console. Okay, this question is about how autoscaling works in Google Kubernetes Engine. To get the right answer, it's important to understand that GKE has a two-level autoscaling system that works together. One for scaling your applications, and one for scaling your infrastructure. First, the horizontal pod autoscaler, or HPA, watches the CPU usage of your application pods. If the load gets high, it creates more pods. Second, the cluster autoscaler watches for pods that can't be scheduled because there's no room. When it sees these pending pods, it adds more nodes or virtual machines to the cluster. With that in mind, let's evaluate our options. Let's look at options C and D. Both are incorrect because they mention the max unavailable and max surge properties. These settings are used to control how a rolling update happens during a deployment. They have nothing to do with autoscaling based on CPU load. Next, option B is also incorrect. While it correctly mentions the horizontal pod autoscaler, it suggests enabling autoscaling directly on the managed instance group. You should not do this. You should always use the Kubernetes native cluster autoscaler, which is designed to work intelligently with the GKE scheduler. This brings us to option A, which describes the correct, complete process. First, you configure a horizontal pod autoscaler to create more pods when CPU usage is high. Then, you enable the cluster autoscaler for your GKE cluster. When the HPA tries to add new pods and there isn't enough space, the cluster autoscaler will see this and automatically add a new node to the cluster to run them. This combination provides a complete, end-to-end autoscaling solution. Therefore, the correct thing to do is A. Configure a horizontal pod autoscaler with a target CPU usage, and enable the cluster autoscaler from the GCP console. Question 109. You need to develop procedures to verify the resilience of disaster recovery for remote recovery using GCP. Your production environment is hosted on-premises. You need to establish a secure, redundant connection between your on-premises network and the GCP network. What should you do? Verify that dedicated interconnect can replicate files to GCP. Verify that direct peering can establish a secure connection between your networks if dedicated interconnect fails. B. Verify that dedicated interconnect can replicate files to GCP. Verify that Cloud VPN can establish a secure connection between your networks if dedicated interconnect fails. C. Verify that the transfer appliance can replicate files to GCP. Verify that direct peering can establish a secure connection between your networks if the transfer appliance fails. D. Verify that the transfer appliance can replicate files to GCP. Verify that Cloud VPN can establish a secure connection between your networks if the transfer appliance fails. Okay, this is a question about designing a resilient hybrid cloud network. The key requirements are that the connection must be secure and, most importantly, redundant, meaning there needs to be a primary connection and a backup connection in case the primary one fails. With that in mind, let's evaluate our options. Let's first look at options C and D, which both suggest using a transfer appliance. This is incorrect because a transfer appliance is a device for offline, bulk data migration. You use it to ship a large amount of data one time. It is not a continuous, real-time connection, which is what you would need for a disaster recovery replication plan. Next, let's look at option A. It correctly identifies dedicated interconnect as a good primary connection. However, it suggests using direct peering as a backup. This is incorrect. Direct peering is for exchanging public internet traffic with Google's network. It's not designed to be a secure, private failover tunnel for your internal corporate traffic. This brings us to option B, which describes the correct and Google-recommended architecture for a redundant connection. You use dedicated interconnect as your primary link. This gives you a high bandwidth, private, and reliable connection for your main data replication. Then, you set up a Cloud VPN as your backup. The VPN runs over the public internet and provides a secure, encrypted tunnel. If your primary dedicated interconnect connection ever fails, your network can automatically fail over to the Cloud VPN to maintain connectivity. This combination provides both high performance and high availability. Therefore, the correct approach is B. Verify that dedicated interconnect can replicate files to GCP and verify that Cloud VPN can establish a secure connection between your networks if dedicated interconnect fails. Question 110. Your company operates nationally and plans to use GCP for multiple batch workloads, including some that are not time-critical. You also need to use GCP services that are HIPAA certified and manage service costs. How should you design to meet Google best practices? Provision preemptible VMs to reduce cost. Discontinue use of all GCP services and APIs that are not HIPAA compliant. B. Provision preemptible VMs to reduce cost. Disable and then discontinue use of all GCP services and APIs that are not HIPAA compliant. C. Provision standard VMs in the same region to reduce cost. Discontinue use of all GCP services and APIs that are not HIPAA compliant. D. Provision standard VMs to the same region to reduce cost. Disable and then discontinue use of all GCP services and APIs that are not HIPAA compliant. Okay, this question combines two important topics: cost optimization for batch workloads and ensuring HIPAA compliance. We need to find the best approach for both of these requirements. With that in mind, let's evaluate our options. Let's first look at the compute resource choice. Options C and D suggest using standard VMs. This is not the most cost-effective choice. The question states that some workloads are not time-critical. For these types of fault-tolerant batch jobs, preemptible VMs, as mentioned in options A and B, are a much better option as they offer significant cost savings. Now let's look at the compliance action. Option A only says to discontinue use of non-compliant services. This is not strong enough. A better security and compliance posture is to actively disable those services, often using an organization policy, to technically prevent their use. This is a more robust approach than simply having a policy to not use them. This brings us to option B, which is the correct answer. Combines the best of both worlds. First, it recommends provisioning preemptible VMs to reduce cost, which is the perfect choice for non-time-critical batch jobs. Second, it recommends to disable and then discontinue use of any non-HIPAA compliant services. This is the strongest and most secure approach to ensuring compliance. This option correctly addresses both cost and compliance. Therefore, the design that meets Google best practices is B. Provision preemptible VMs to reduce cost, and disable and then discontinue use of all GCP services and APIs that are not HIPAA compliant. Question 111. You want to automate the creation of a managed instance group. The VMs have many OS package dependencies. You want to minimize the startup time for new VMs in the instance group. What should you do? A. Use Terraform to create the managed instance group and a startup script to install the OS package dependencies. B. Create a custom VM image with all OS package dependencies. Use Deployment Manager to create the managed instance group with the VM image. C. Use Puppet to create the managed instance group and install the OS package dependencies. D. Use Deployment Manager to create the managed instance group and Ansible to install the OS package dependencies. Okay, this is a question about optimizing the process of creating new virtual machines, specifically how to make them start up as quickly as possible. The key problem to solve is how to handle the many OS package dependencies without slowing down the boot process. With that in mind, let's evaluate our options. Let's look at the options that involve installing software during startup, which are A, C, and D. These options suggest using tools like startup scripts, Puppet, or Ansible to install the dependencies every time a new VM is created. While these tools are great for automation, this approach directly conflicts with the goal of minimizing startup time, because the installation process itself takes time. This brings us to option B, which describes the correct and Google-recommended best practice for this scenario. The strategy is to pre-bake a custom VM image. First, you create a custom image that already has all of the OS package dependencies installed on it. Then, you use an infrastructure as code tool like Cloud Deployment Manager to automate the creation of your managed instance group, telling it to use your new custom image. When the instance group needs to create new VMs, they are created from an image that is already configured and ready to go, which drastically reduces their startup time. Therefore, the best way to minimize startup time is B. Create a custom VM image with all OS package dependencies, and use Deployment Manager to create the managed instance group with the VM image. Question 112. Your company wants to try out the cloud with low risk. They want to archive approximately 100 terabytes of their log data to the cloud and test the analytics features available to them there, while also retaining that data as a long-term disaster recovery backup. Which 2 steps should you take? Choose 2. Create a group per country. Add analysts to their respective country groups. Create a single group, all_analysts, and add all country groups as members. Grant the all_analysts group the IAM role of BigQuery job user. Share the appropriate dataset with view access with each respective analyst country group. B. Create a group per country. Add analysts to their respective country groups. Create a single group, all_analysts, and add all country groups as members. Grant the all_analysts group the IAM role of BigQuery job user. Share the appropriate tables with view access with each respective analyst country group. C. Create a group per country. Add analysts to their respective country groups. Create a single group, all_analysts, and add all country groups as members. Grant the all_analysts group the IAM role of BigQuery data viewer. Share the appropriate dataset with view access with each respective analyst country group. D. Create a group per country. Add analysts to their respective country groups. Create a single group, all_analysts, and add all country groups as members. Grant the all_analysts group the IAM role of BigQuery data viewer. Share the appropriate table with view access with each respective analyst country group. Okay, this is an identity and access management question for BigQuery. The challenge is to give different teams access to their own specific datasets, while making sure they can't see the data of other teams. The key to solving this in BigQuery is to separate 2 different types of permissions. First is the permission to run a query, which is a job. Second is the permission to actually read the data in a specific dataset. A user needs both of these to successfully analyze their data. With that in mind, let's look at our options. Let's look at options C and D. Both of these are incorrect because they grant the BigQuery data viewer role to the main group of analysts. This role allows users to see data, but it does not give them the necessary permission to run query jobs, so they wouldn't be able to perform their analysis. Next, let's look at option B. While it correctly grants the BigQuery job user role, it suggests sharing access at the table level. The question states that the data is already neatly organized with 1 dataset per country. Therefore, it's much simpler and more efficient to grant access at the dataset level rather than managing permissions for every single table individually. This brings us to option A, which describes the correct and recommended best practice. It follows a perfect model. First, you grant the BigQuery job user role to a group containing all analysts. This gives everyone the general ability to run queries. Then, for each specific country's analyst group, you share view access only to their respective dataset. This combination ensures that to successfully query data, an analyst must have both the general permission to run a job and the specific permission to view their country's dataset, while being blocked from seeing any other country's data. Therefore, the correct way to configure the access rights is a create a group per country. Add analysts to their respective country groups. Create a single group, all_analysts, and add all country groups as members. Grant the all_analysts group the IAM role of BigQuery job user. Share the appropriate dataset with view access with each respective analyst country group. Question 113. Your web application uses Google Kubernetes Engine to manage several workloads. One workload requires a consistent set of host names even after pod scaling and relaunches. Which feature of Kubernetes should you use to accomplish this? Stateful sets. B. Role-based access control. C. Container environment variables. D. Persistent volumes. Okay, this is a question about Kubernetes workloads. The key to this question is the requirement for a consistent set of host names. This tells us that the application is stateful and needs a stable network identity, which is a very specific requirement in the Kubernetes world. With that in mind, let's look at our options. Let's start with option B, Role-Based Access Control, or RBAC. This is incorrect. RBAC is a security feature used to control who has permission to do what within the cluster. It has no impact on how pods are named or addressed on the network. Next, option C, Container Environment Variables. This is also incorrect. Environment variables are a way to pass configuration settings into your application inside the container, but they don't control the hostname that Kubernetes assigns to the pod itself. Option D is persistent volumes. While persistent storage is a crucial part of most stateful applications, it's responsible for providing a stable identity for the storage, not for the pod's network identity or hostname. This brings us to option A, which is the correct answer. A stateful set is a special type of Kubernetes workload object designed specifically for stateful applications, like databases or message queues, that need stable identities. Unlike a standard deployment where pods are interchangeable, a stateful set gives each pod a unique and predictable hostname, like myapp0, myapp1, and so on. This hostname sticks with the pod's identity even if it gets restarted or rescheduled, perfectly fulfilling the requirement for a consistent set of hostnames. Therefore, the Kubernetes feature you should use to accomplish this is A. Stateful sets. Question 114. You are using Cloud CDN to deliver static HTTPS website content hosted on a compute engine instance group. You want to improve the cache hit ratio. What should you do? A. Customize the cache keys to omit the protocol from the key. B. Shorten the expiration time of the cached objects. C. Make sure the HTTPS header cache region points to the closest region of your users. D. Replicate the static content in a cloud storage bucket. Point Cloud CDN toward a load balancer on that bucket. Okay, this is a question about optimizing the performance of Cloud CDN. The goal is to improve the cache hit ratio, which means we want the CDN to serve content from its cache more often, instead of having to go back to our origin servers. With that in mind, let's evaluate our options. Let's start with option B, shortening the expiration time. This is incorrect because a shorter expiration time would cause the CDN to discard cached objects more frequently, forcing it to fetch them from your server more often. This would actually decrease the cache hit ratio. Next, option C suggests using a cache region header. This is also incorrect as this is not a standard HTTP header that Cloud CDN uses for its caching logic. The CDN automatically determines the best location to serve content from. Option D suggests replicating the content to a cloud storage bucket. While using cloud storage as an origin for static content is a good practice, simply replicating the data doesn't solve the core issue of why the cache hit ratio might be low. The CDN is already designed to distribute content globally. This brings us to option A, which is the correct solution. By default, Cloud CDN uses the entire URL, including the protocol like HTTP or HTTPS, to create a unique cache key. This means if the same image is requested over both HTTP and HTTPS, the CDN treats it as two separate files and creates two different cache entries. By customizing the cache keys to omit the protocol, you tell the CDN to ignore the HTTP versus HTTPS part and treat them as the same object. This consolidates requests for the same content into a single cache entry, which directly improves the cache hit ratio. Therefore, the best way to improve the cache hit ratio in this scenario is A. Customize the cache keys to omit the protocol from the key. Question 115. Your architecture calls for the centralized collection of all admin activity and VM system logs within your project. How should you collect these logs from both VMs and services? All admin and VM system logs are automatically collected by Stackdriver. B. Stackdriver automatically collects admin activity logs for most services. The Stackdriver logging agent must be installed on each instance to collect system logs. C. Launch a custom syslogged compute instance and configure your GCP project and VMs to forward all logs to it. D. Install the Stackdriver logging agent on a single compute instance and let it collect all audit and access logs for your environment. Okay, this question is about how log collection works in Google Cloud. The key to getting this right is to understand that there are two different types of logs. Logs from the cloud platform itself, and logs from inside your virtual machines, and they are collected in different ways. With that in mind, let's evaluate our options. Let's start with option A. It claims that all admin and VM system logs are collected automatically. This is incorrect. While Google Cloud does automatically collect admin activity logs, it does not automatically collect the system logs from inside your VMs. Next, let's look at option C, which suggests building your own custom logging server. This is not a recommended practice. It requires you to manage your own infrastructure for logging, which is less scalable and more work than using the fully managed cloud logging service that Google provides. Option D is also incorrect. It suggests installing the logging agent on a single VM to collect logs from the entire environment. The agent only works on the machine it's installed on. It cannot collect logs from other VMs. This brings us to option B, which accurately describes how log collection works. Admin activity logs, which are generated by Google Cloud Services, are indeed collected automatically by cloud logging. However, to collect the system logs from inside your virtual machines, you must install the cloud logging agent on each of those instances. The agent is responsible for sending those internal logs to the central cloud logging service. This two-part approach is the standard, recommended practice. Therefore, the correct way to collect these logs is B. Stackdriver automatically collects admin activity logs for most services, and the Stackdriver logging agent must be installed on each instance to collect system logs. Question 116. You have an App Engine application that needs to be updated. You want to test the update with production traffic before replacing the current application version. What should you do? A. Deploy the update using the Instance Group Updater to create a partial rollout, which allows for canary testing. B. Deploy the update as a new version in the App Engine application and split traffic between the new and current versions. C. Deploy the update in a new VPC and use Google's global HTTP load balancing to split traffic between the update and current applications. D. Deploy the update as a new App Engine application and use Google's global HTTP load balancing to split traffic between the new and current applications. Okay, this question is about safely deploying updates to a Google App Engine application. The main goal is to test a new version with real user traffic before sending everyone to it. This is a strategy often called a canary release. With that in mind, let's look at our options. Let's start with option A. This is incorrect because the Instance Group Updater is a feature for managing virtual machines on Compute Engine, not for deploying applications on the App Engine platform. Options C and D are also incorrect because they are overly complicated. You don't need to create a new VPC or an entirely new App Engine application just to test an update. App Engine has powerful, built-in features to handle this much more simply. This brings us to option B, which describes the correct and recommended practice for App Engine. The platform is designed to run multiple versions of your application at the same time. You can deploy your update as a new, separate version while the old version continues to handle all the user traffic. Then, using the built-in traffic splitting feature, you can direct a small percentage of your users, like 1%, to the new version. This allows you to test it safely with live traffic. If everything looks good, you can gradually increase the traffic to the new version until it's handling 100%. Therefore, the correct thing to do is B. Deploy the update as a new version in the App Engine application and split traffic between the new and current versions. Question 117. All Compute Engine instances in your VPC should be able to connect to an Active Directory server on specific ports. Any other traffic emerging from your instances is not allowed. You want to enforce this using VPC firewall rules. How should you configure the firewall rules? A. Create an egress rule with priority 1000 to deny all traffic for all instances. Create another egress rule with priority 100 to allow the Active Directory traffic for all instances. B. Create an egress rule with priority 100 to deny all traffic for all instances. Create another egress rule with priority 1000 to allow the Active Directory traffic for all instances. C. Create an egress rule with priority 1000 to allow the Active Directory traffic. Rely on the implied deny egress rule with priority 100 to block all traffic for all instances. D. Create an egress rule with priority 100 to allow the Active Directory traffic. Rely on the implied deny egress rule with priority 1000 to block all traffic for all instances. Okay, this is a network security question about how VPC firewall rules work in Google Cloud. The key to solving this is to understand how rule priorities are evaluated. The most important rule to remember is that firewall rules are processed in order of their priority number, and a lower number means a higher priority. The first rule that matches the traffic is the one that gets applied. With that in mind, let's look at our options. Let's look at option B. It suggests a deny rule with a high priority of 100 and an allow rule with a lower priority of 1000. This is incorrect because the deny rule would be checked first, and it would block all traffic, including the Active Directory traffic we want to permit. The allow rule would never even be considered. Next, let's look at options C and D. Both of these are incorrect because they misstate the priority of the implied deny egress rule. While there is an invisible rule that denies all egress traffic that isn't explicitly allowed, its priority is 65,535, which is the lowest possible. The priorities mentioned in these options are wrong. This brings us to option A, which describes the correct configuration. You create two rules. First, an allow rule for the specific Active Directory traffic with a high priority, like 100. Second, you create a deny all rule with a lower priority, like 1000. When a VM tries to connect to Active Directory, the firewall sees the high priority allow rule first and lets the traffic through. For any other type of traffic, it won't match the first rule, so it will continue down the list and get blocked by the lower priority deny rule. This is the standard way to implement a deny by default policy. Therefore, the correct way to configure the firewall rules is a create an egress rule with priority 1000 to deny all traffic for all instances, and create another egress rule with priority 100 to allow the Active Directory traffic for all instances. Question 118. Your customer runs a web service used by e-commerce sites to offer product recommendations to users. The company has begun experimenting with a machine learning model on Google Cloud Platform to improve the quality of results. What should the customer do to improve their model's results over time? A. Export Cloud Machine Learning Engine performance metrics from Stackdriver to BigQuery to be used to analyze the efficiency of the model. B. Build a roadmap to move the machine learning model training from cloud GPUs to cloud TPUs, which offer better results. C. Monitor compute engine announcements for availability of newer CPU architectures, and deploy the model to them as soon as they are available for additional performance. D. Save a history of recommendations and results of the recommendations in BigQuery to be used as training data. Okay, this is a question about the machine learning lifecycle. The core task is to find the best way to improve the quality of the model's results over time, not just its speed or efficiency. With that in mind, let's look at our options. Let's start by looking at the options related to hardware, which are B and C. Moving to faster hardware like TPUs or newer CPUs can make your model train faster or serve predictions with lower latency, but it doesn't inherently make the model's recommendations more accurate. The quality of a model depends on its data and algorithm, not the speed of the chip it runs on. So these are incorrect. Next, option A suggests analyzing performance metrics. This is also incorrect for this specific problem. Analyzing metrics like CPU usage helps you understand the operational efficiency of your model, but it tells you nothing about whether the recommendations it's making are good or bad. This brings us to option D, which is the correct solution. This describes the process of creating a feedback loop, which is essential for improving any machine learning model over time. You save the recommendations that the model makes, and you also save the results. Did a user click on the recommendation or buy the product? This new data is incredibly valuable. By using this history of results as new training data, you can periodically retrain your model, allowing it to learn from its successes and failures and adapt to new trends. This is the fundamental way to improve a model's quality. Therefore, the correct thing to do is D. Save a history of recommendations and results of the recommendations in BigQuery to be used as training data. Question 119. You need to design a solution for global load balancing based on the URL path being requested. You need to ensure operations reliability and end-to-end in-transit encryption based on Google best practices. What should you do? A. Create a cross-region load balancer with URL maps. B. Create an HTTPS load balancer with URL maps. C. Create appropriate instance groups and instances. Configure SSL proxy load balancing. D. Create a global forwarding rule. Configure SSL proxy load balancing. Okay, this is a question about advanced load balancing on Google Cloud. We need to find a solution that is global, can route traffic based on the URL path, and provides end-to-end encryption. With that in mind, let's evaluate our options. Let's start with options C and D, which both suggest using SSL proxy load balancing. This is incorrect. The SSL proxy load balancer operates at layer 4 of the network stack. This means it can't see the application-level details like the URL path. Since the requirement is to route based on the URL path, we need a layer 7 load balancer, so these options are not a fit. Next, let's look at option A. While it correctly mentions a cross-region load balancer and URL maps, it's incomplete because it doesn't specify the use of HTTPS, which is crucial for meeting the end-to-end encryption requirement. This brings us to option B, which is the correct and complete solution. An HTTPS load balancer is Google's global Layer 7 load balancer. The HTTPS part ensures that traffic is encrypted between the user and the load balancer, and it can be configured to also use HTTPS to the backends for end-to-end encryption. The URL maps component is the specific feature that allows the load balancer to inspect the URL path and route requests to different backend services. This combination perfectly meets all the requirements of the question. Therefore, the correct thing to do is B. Create an HTTPS load balancer with URL maps. Question 120. Your company has an outage in your Compute Engine Managed Instance group. All instances keep restarting after 5 seconds. You have a health check configured, but auto-scaling is disabled. Your colleague, who is a Linux expert, offered to look into the issue. You need to make sure that he can access the VMs. What should you do? Use gRPC instead of HTTP for better performance. B. Implement retry logic using a truncated exponential backoff strategy. C. Make sure the cloud storage bucket is multi-regional for geo-redundancy. D. Monitor https //status.cloud google.com/feed.atom https://status cloud google.com/feed.atom, and only make requests if cloud storage is not reporting an incident. Okay, this is a question about building a resilient application that can handle the temporary errors that are common in distributed cloud environments. The key to this question is recognizing what the HTTP error codes 5xx and 429 mean. A 5xx error is a generic server-side error, and a 429 error means too many requests. Both of these are typically transient, meaning the problem is temporary. The best way to handle temporary problems is to wait a short while and try again. With that in mind, let's look at our options. Let's start with option A, using gRPC instead of HTTP. This is incorrect. Changing the protocol doesn't change the fact that the server is temporarily busy or that you're being rate limited. The same kind of errors can happen over gRPC. Next, option C, making the bucket multi-regional. This is a good practice for data availability, but it doesn't prevent your application from hitting rate limits or encountering temporary server issues, so it doesn't solve this specific problem. Option D suggests monitoring the Google Cloud status page. This is not a practical solution for an application. These types of granular, temporary errors are often not reflected on the global status page, and your application shouldn't have to stop working every time it encounters a recoverable error. This brings us to option B, which is the correct and universally recommended solution. You should implement a retry logic with a truncated exponential backoff strategy. This means when your application sees a temporary error like a 5xx or 429, it doesn't immediately fail. Instead, it waits for a short, increasing amount of time before trying the request again. This backing off gives the server time to recover and greatly increases the chance that the retry will succeed. It's the standard way to build robust cloud applications. Therefore, the way you should handle these errors is B. Implement retry logic using a truncated exponential backoff strategy. Thanks for watching. If you found this video interesting and helpful, please like, share, and subscribe to our channel. See you in the next video. Happy learning!